Well, thank you very much. Can you hear me? Is this on? Oh, okay. It's a pleasure to be here back in Cambridge. New campus to me. This is very nice. And privileged to talk with all of you. Gwendolyn said that he was maybe the third oldest speaker. I think I can beat him there. In fact, I'm from the classical function theory area originally. And so I can say that at my typical conference nowadays, the average age is about 3 times the average age here. That's refreshing, but unless you get complacent, look forward to a time when you might be able to say the same thing. So I want to talk about something that's a little different and, in a sense, deterministic most of the way. So I'm going to start with a few pictures of classical, what I call traditional conformal tiling. This is an infinite tiling of the plane by tiles, all have the same Euclidean shape. These are aperiodic. There's no global symmetries in the pattern. One of the keys, though, is that the eye picks out local symmetries. The most famous one, perhaps, is the Penrose tiling in the form of kites and darts. Dimer tilings. This is not particularly a subdivision type, but they could be subdivision type tilings. And so tilings do have other forms. We're going to talk largely about ones obtained by some type of subdivision process. Hence the feeling that it's deterministic. Why at this workshop? I don't know, I just take it as a blessing to be able to come here, but I hope to connect it up in some ways. First of all, this derives from pure combinatorics in a sense at the beginning, and the complexities in combinatorics, which you know well. There's a conformal structure which is added in a sense as a convenience to give you tools to work with that combinatorial structure. And so conformal structure, a wonderful thing. And so if you can bring it into a topic, it brings perhaps a lot of tools along. And those who know me know that circles lurk somewhere behind this topic for me. And so in actual experiments and implementation, these tilings are built using circle packing. And I'll just say a little about that, but it is behind all the pictures. It's experimentally driven. So it's a case in which you actually do real experiments, much like physicists get to do. And you see things, I tell people that in my experimental world, you start running experiments to investigate property A, and as soon as you do the first, most naive experiment, property B appears unexpected, and you find that that's much more interesting than property A in any case. And so experiments bring a whole new tenor to the work. Randomness, well, I hope to get to that at the end, but that's sort of in an inverted sense. And so I want to talk at the end about randomness at the ends of these infinite patterns. And of course, beautiful pictures is part of this topic. I hate to admit that how much we depend on those beautiful pictures for interest. So I'm going to talk about the basics of conformal tiling. It's a new topic in a sense, and then a little about the practice, very little. Talk about subdivision rules. Then I'll outline a little of the traditional theory. And so the idea in this new version of tiling is in part to follow the parallels with the traditional theory and see what we can get in this new setting, and to connect it to other things. Then I'll talk about hierarchies and those potentially random ends of these hierarchies. So in conformal tiling, I picture these structures layered on top of it. There's the underlying combinatorial structure. We'll have complexes that give us just the combinatorics. Then we'll put a conformal structure on those. We get a metric structure out of a little function theory, and then we get a geometric structure out of the Riemann mapping theorem. So the combinatorics, this looks geometric, but think of this as a freehand drawing. We're going to start out with polygonal complexes in the plane. So these are abstract drawings, if you will, where the faces are these tiles, n-sided tiles. There's a dual graph, a dual to this drawing. And if you take those two together, there's a quad pattern underneath, the blue quads. And we use all three of these, and we break this into a triangulation. So this is the fundamental geometric starting point for me. Now, I don't know from here, I can't see it, but some of these are gray and some are white. So it's a pattern of white and gray triangles. You put those triangles together in various ways to get the original tiling, or to get the dual tiling, or to get the quad tiling. So all of them are just sort of interlinked. Underlying all of them is this one triangulation. So that's the combinatorics. We put a conformal structure in by giving each triangle an equilateral triangular structure. So think of each one as a Euclidean equilateral triangle. You have a pattern, you paste these equilateral triangles together. That gives you a Riemann surface. And so there's an example with 10 triangles pasted together. But of course it has these cone points where something other than 6 triangles come together. It's not flat, but it's perfectly good as a Riemann surface. And you get a conformal structure there by using power maps near the cone points to flatten things out. And so it's conformally, this structure is conformally regular and reflective. Those are the two key properties you need out of the structure on a triangulation. And so I have a mistake here. There should be an even number of triangles here, of course. These are the gray and white triangles put together at a vertex. And so that's a conformally regular tile. Each face ends up to be a conformally regular n-gon. But in putting conformal structure on it, you have reflections across edges. And so that reflective structure and the conformal regularity sort of uniquely determines up to Möbius transformations the conformal structure, up to automorphisms. So we get a Riemann surface now with a conformally regular set of polygons, the reflective structure, and the correct pattern of tiles. I want to put a metric structure on here because in the long range I think this metric structure is going to help us get more in this conformal setting of the things that you see in the Euclidean setting where you actually have the Euclidean translations and things around. We don't have those here. But you map each white triangle to one hemisphere, each gray triangle to the other hemisphere. Each of these triangles has vertices that belong to one of 3 cohorts. And we label those 1, 0, and infinity. Map those triangles to the hemisphere. And I robbed this picture from a place where this is shown discretely using circle packings. But for our purposes, forget the circles. You take these hemispheres, and they're pasted together across one of the 3 segments of that great circle. And so you have infinitely many triangles. You paste them together, each now as a hemisphere. And then you get a infinite sheeted cover of the sphere. And so that defines a meromorphic function because each of those maps was conformal. It's reflective, so that carries across the pastings. And we get a meromorphic function m on the surface mapping to the sphere. And you can actually look at these meromorphic functions separately. So they have branch values lying in 0, 1, infinity. They, in this sense, they're sort of infinite extensions of Grothendieck-Dessin maps, the meromorphic functions associated with drawings on compact surfaces, but now we have infinite drawings. It's simply branched at every preimage of the point 1, and it has no asymptotic values, which gives the compact sets that are associated with the tiles. So tilings are in one-to-one correspondence with these meromorphic functions, and so the tiling itself is represented as the inverse image of 0, 1 for this meromorphic function. And the dual tiling is the inverse image of 1 infinity. 1 infinity, and the quad tiling is sort of in there as well. So the meromorphic function, in a sense, has all the information about the tiling for you. But that isn't what we generally talk about on the sphere. We want to put this tiling out, and so we have the Riemann mapping theorem. We're going to take the simply connected case, although I'd like to point out that one of the features of conformal tiling is you can do this on surfaces. So you can have mobily connected surfaces, higher genus surfaces, and so on. But we're going to do the infinite simply connected case. But in any case, you have a uniform uniformization map carrying your Riemann surface to one of the plane, the disk, or the sphere. And what you do is on this Riemann surface, you have all these tiles marked. So you just carry that marking along, and then you get concrete geometric shapes in one of these 3 geometries. And that's our conformal tiling. So we've taken abstract combinatorial tiling and put this conformally regular thing on and now mapped it down to concrete geometric tilings. So those are the tilings I'm going to look at, and I'll actually give some of the examples of the new version, the conformal version of those classical traditional tilings. But here's just a small set of examples in each of the geometries. This is called a Fibonacci fusion tiling by Lorenzo Sedun and Natalie Frank. This is one of these Dasa on the sphere. So it's the same type of structures built in using the same type of triangulation. And here's a hyperbolic version. Now, in all of these, there's a major difference with the traditional Euclidean tilings. And you see it evidently here that the tiles don't have the same shapes. Even tiles of the same number of sides are different. It's less evident here, but what I'll point out in a second is this might look just like a sort of binary decomposition, a Whitney cube decomposition of the upper half plane. So think of this as though it were, identify it with the unit disk if you prefer. But that's much more complicated than you first think. And it turns out that these tiles, so we have a tile here, which may look like that tile over there or look like this tile down here, but in fact, every tile has a completely unique shape. So these tile shapes are unique to each tile and generate the rest of the tiles by Schwartz reflection. So I've just built a small example. This is from the conformal version of the Penrose tiling. So you start with a tile. So these are very subtle analytic arcs bounding this tile. So subtle that if you reflect across one by Schwartz reflection, you get a unique shape for the neighbor, unique shape for that neighbor. So you just go and continually reflect these around, and ultimately you get an infinite tiling of the plane. And so if we go back to that upper half plane thing, each of those tiles is completely unique. If you take one of them and generate this reflection process, you get all the other tile shapes as reflections eventually of that one original. So this is quite a distinction from the traditional tilings, where you have a finite number of prototype shapes, and every tile is Euclideanly isomorphic to one of those. So these are all distinct shapes. Now, how do you do this in practice? This is just very brief. I want to say that there are circle packings lying under all these shapes. And so there's a sort of coarse level packing. You see the tiling shape beginning to emerge. And if you want a better shape, you refine the tiling refine the triangulation, circle pack it, and pick out the shape with more refinement. So all these pictures are obtained this way with circle packings. And I don't think in this group we have to advertise about circle packing because so many people are familiar with it and use it. But the experiments are the key both to the intuition and to the theory when you try to run things and see what's happening. In circle packing, as far as I know, absolutely the only way you can see these shapes. And the circle packings have a discrete theory which is essentially completely parallel to the continuous theory. So in circle packing, this is very common. You discretize something, and at the discrete level, you get structures which not only immediately mimic the continuous structures, but in the limit, under refinement, actually converge to them. So in a way, you can depend on circle packings quite generally to give the right behavior, even at the coarse level, before you've worked hard to get actual approximations. And that's the case here. So in between the combinatorics and this conformal structure, the ultimate conformal structure that's perfectly good in theory, in practice there's this intermediate discrete theory with circle packing. So this is the chair tiling. And to remind you, I put a little copy of the chair tiling. So this, in each of these tiles, since some of them meet in the edges of other tiles, you have to treat each tile as an octagon. And so this is just a pattern of octagons identified, sometimes with two edges being shared, sometimes with just one edge being shared. And so this pattern of octagons, when you put the conformal structure on it, gives this pattern in the plane. Now, there is not a single straight line in this anywhere. So these look like sort of squares, but they're not. There are some extra edges that are hidden because they're in the middle of a line where two tiles meet. So those are analytic arcs. There are many things, to be honest with you, that we don't know about the long-term behavior of this. So for example, I don't know that the tiles in this infinite conformal tiling will actually be bounded, universally bounded in diameter in the plane. I mean, there are many questions about these tilings, so I don't want to give the impression that that we know all the details. But we're pursuing that, and in addition, there's the question, which is a key part of the conformal theory, as to whether your Riemann mapping takes you to the plane or the hyperbolic plane. You know, is it the plane or is it in the hyperbolic in the disk? This tiling we can prove is in the plane, but we just don't know some fundamental details about it. This is the Penrose tiling, and seeing this, I think you're reminded quite nicely of the Euclidean version. But notice that the kites aren't very kite-like. The darts are okay, but the kites aren't even convex. So there are a lot of changes, but the eye immediately sort of picks out the pattern here as being similar. And one of the things about this theory which is yet to be discovered is whether hidden in the conformal one under certain types of refinements we'll talk about, you can actually see in the limit the traditional one. I may say a little more about that down the road. This is the pinwheel tiling. John Conway's tiling that breaks, in the Euclidean case, breaks this triangle into 5 similar triangles, this right triangle. Conformally, there's quite a lot of pattern you start seeing in here. So they're intriguing for their own purposes when you look at the underlying patterns that your eye picks out. This is that particular dimer tiling. So again, there's a unique shape for every one of these dimers. subdivision rules. So this is the Robinson tile subdivision rule for the Penrose tiling. You have 4 types of tiles, 2 types with different orientations on each type. And this is a rule that tells you how to break each type down into copies, pieces of the original. Now this is not intended to be geometric, but it is geometric if you put the Euclidean structure on it. But for us, it's just the combinatorics of how you subdivide something. And so a little about that traditional theory. It's about infinite patterns of Euclidean shapes. And here we're concerned with the parallel conformal situation. So there are a few traditional notions that are sort of keys to make things work. Traditionally, there are finitely many Euclidean shapes. Well, that's out the window. There are uncountably many, countably many different shapes, uncountably many if you consider all tilings of a given pattern. Finite local complexity is the type of thing you're used to encountering when you have to extract limits from growing patterns of combinatorial objects. These are aperiodic, so there's no infinite order symmetries. We're not looking at things like you can tile your bathroom floor with. We're looking at things that have no global symmetries. Yet there's a hierarchical structure, a sort of the eye picks out and looks at this and says, oh, that pattern looks a lot like it does over here. There are no global symmetries, so it's not the same as the one over there. Where do they differ? But the eye picks these things out. What is that? Oh, is this power source not on? My battery will go with this. How do I get power? Oh, it's not plugged in, that's why. Is this on? Where does this plug in? Here.
Yeah, just a second. Is that better?
Did it go away? Yeah. Okay. Oh, thank heavens. Okay. So, where was I? Local isomorphisms. So what we'll find is that these complexes have a lot of local isomorphisms. In fact, uniformly distributed around the pattern. Now, most of these are generated by these subdivision rules, like the Penrose I mentioned. Now, the thing is that subdivision rules in the traditional setting it's very rare that you can find a pattern and know how to subdivide it and apply a rule. So that's one of the beauties of the patterns that have been discovered. You know, the chair, the sphinx, the pinwheel, the Penrose, etc. So there are a few, but the advantage, it seems, on the conformal side is that I can do anything I want with the combinatorics. You give me any triangulation, you know, I'll get this conformal structure I can put on it. So really any pattern works and any type of subdivision works. But that seems to be an advantage at first, but I want to give you a tale of 2 subdivision rules. Forget this little X here, that was just a detail. But this is the Sphinx that has 2 types of tiles, each broken by the subdivision into 4 among those 2 types. And so you can do this Euclideanly. Here's another one, though. It's called the lace rule, and I show it. This applies to any n-gon, but we'll just have 3 gons, 4 gons, and 5 gons we have to apply it to. And when you apply it, for example, to a 5-gon, you end up with 5 gons, 4 gons, and 3 gons. And so you can then apply this rule again to those. So that's the notion of subdivision. I have this pattern of tiles. I know how to break each one apart. I get a new pattern of subdivided tiles. Then I apply the rule again, again, and again. So here's the Sphinx. And so this is an infinite tiling with that Sphinx pattern, but I've grouped some of the ones that came from a single sphinx under subdivision. So I hope you can see these darker lines. That's a sphinx tile at one stage, which was subdivided, it looks about 4 times. And then the conformal structure was put on that subdivided pattern. And the thing is that the original tile no longer has the shape it started with, unlike the Euclidean setting. I want to compare that with the lace. Here's a lace tiling, this large one. And it was broken down into subtiles according to that subdivision rule. And each of those was broken down further into subtiles. But the thing is here that if I take the conformal structure on the finest set of tiles here, and I use that to define my conformal structure, it gives the correct conformal structure even to the aggregate tiles. So unlike with the Sphinx, it depends on when I put the conformal structure on. If I put the conformal structure on and then subdivide and put a conformal structure on the finer pattern, the original shapes are lost. But here the original shape persists. So to get some of the parallels to the classical theory, we're going to have to limit ourselves to tilings that we call conformal, subdivision rules rather, that we term as conformal for this property. So that means that I can, just like the traditional setting, I can subdivide in situ and see my finer and finer tilings all in the same picture. And so that one is particularly nice. That's a conformal subdivision rule. And so here I started with one square tile, one 4-sided tile. I applied the subdivision rule, and you see the blue, the large blue. I applied the subdivision rule. So if I had done just that one rule and put the conformal structure on and made it a square by specifying the boundary values to be a square, you would see those blue shapes. When I subdivide it, I have many more tiles. I put the conformal structure on there and again put it in a square. The blue ends up in the same spot, but I now have subtiles, the green ones. So is everybody with me? I get to, with conformal tiles, subdivide in place, and the conformal structures are compatible from one tile to its subdivision.
Sorry, these pieces have different numbers of sides. How do you...
Yes. This is, so there's a 4-sided, there's a 5-sided. All of them in here are 4-sided or 5-sided. This tile, for example, is a 5-sided tile. So the blue is part of its, is 2 of its edges, then there's 3, 4, 5 edges. So every one of the tiles in this picture is 3 or 4-sided at every refinement level. Does that answer your?
And then you have a different rule for how to divide the 3s and the 4s?
Yeah, the rule is this. This tells me how to divide a 4 into 3, 4s, and 5s.
All right, okay.
How to divide a 5 into 3, 4, and 5s, and so on. The thing about this rule is, I haven't shown it, but really, if I drew a dotted line to the center here and a dotted line, there's a subdivision rule for each segment, and it's symmetric. So use a subdivision for 3 segments, use a subdivision for 4 segments here, or for 5 segments, you get the same subdivision rule. Phil Bowers, my co-author, and I call these subdivision operators. So what is some of the structure behind this? Well, at the combinatoric level, there are these complexes and their spaces. So our complexes, the combinatorics is encoded in these planar polygonal complexes, which we call K. There's types of conditions we need involve local finite complexity. So in these tilings, no more than a certain number of edges on any tile. So an upper bound on the number of edges of any tile, and an upper bound on the number of tiles that meet at any vertex. Combinatorially, you have to throw in some additional things that you don't have. Why did that appear there? Huh? We'll see. I'm new to PowerPoint, so excuse me. So there are some additional things that the geometry helped you with in the traditional tiling. So isometric inequalities or isoperimetric inequalities are one of those things that we have to sort of include separately in the combinatorics. And then there's a uniformly repetitive property. And I'll say something about that in a second. So we actually have spaces of these tilings, as you might imagine. So C is the isomorphism classes. So this is purely orientation preserving isomorphism class of the complexes. But as is typical, you have to start talking about rooted ones when you talk about a topology on these. So we put a metric space topology on the rooted isomorphism classes, where we use what in that field they call the big ball metric. So I don't know the term, the neighbor, uniform neighbor metric, or there are other terms and other topics, but the idea is that combinatorially you look at a ball around a point and compare to what radius you have to go to for those balls to be isomorphic, and that gives you a measure of the distance between those two rooted complexes. So the same type of thing used here, you get this space of rooted isomorphism classes. And then we have, there's why it's, see, I was prepared for that. So you have the rooted local isomorphism classes. So what happens in a lot of these patterns is you have local areas that are isomorphic for quite a while, but of course there are no global isomorphisms in general, and so you define the local isomorphism class by saying that two are locally isomorphic if every finite subclass of subcomplex of one embeds in the other, and vice versa. So every finite patch, no matter how large in one, can be found in the other, and vice versa. And then the uniformly repetitive is the notion that you have a complex in which every large piece of it can be found in that complex with uniform density. So given some large piece, there exists a radius so that every point in the complex, every face in the complex, if I take a ball of that radius, it has a copy of that piece in it. And so when you're working with these subdivision rules, under minor conditions, you get these sort of things automatically. So that brings us to the hierarchies. So the aperiodic tilings have no global symmetries, but we're talking about what the eye picks out. I don't know, there are certain topics that attract you. I mean, the Penrose tiling is famous because it just grabs your attention. You sort of see patterns in there, and you look away and you look back and you may not find that one, but you see some other pattern in it. So the eye is picking out these sort of self-similar pieces, and the sort of scale invariance that we saw with the lace tiling, where I see it at different levels, the same type of pattern. And so hierarchy sort of tries to capture this. So certain subdivision operators lead to combinatorial hierarchies. So this is purely in the combinatorics, where you have a double infinite chain of complexes, each one a planar polygonal complex, with the property that each one is the subdivision combinatorially of the previous one. And moreover, where each one is locally isomorphic to every other one. So this hierarchy is what we want to look at. This hierarchy is rather, it's not deterministic. If you start with a complex K and you have this subdivision rule, well, I mean, then it's deterministic, determining K1 and then apply the subdivision rule, get K2, etc. It's going the other way that is the issue. And so sort of the argument is basically this. I look at K and I'd like to find something that subdivides to give K. Well, a large piece of K lies within this subdivision of itself. And so over in the subdivision of itself, I see not only K, but I see some of its prehistory, or what could be its prehistory. So I slide that back, and that becomes part of this prehistory. And so I can do this at various stages and extract limits to build this infinite chain of prehistories for my complex. Well, if you have a conformal rule, then this is a conformal hierarchy. That is, I have for each combinatoric situation, I have the corresponding conformal tiling. And when I subdivide the complex, I can subdivide the tiling in place, and I get a new tiling with the combinatorics of the original of K1. And so I can subdivide these in place, and likewise I can sort of aggregate them in place, although the aggregation has to come out of this process of building this prehistory. So this subdivision allows me to sort of run a movie both ways. Now there are properties that I'm not going to go into. Certain tilings, certain subdivision rules, for example, are conformal. But which ones are conformal? Well, we haven't built much of a catalog yet. There is certain dihedrally symmetric rules which are conformal, and so we have examples, I think non-trivial examples to show this goes on. The very first conformal tiling was more or less the pentagonal, regular pentagonal tiling of the plane that Phil Bowers and I built back in '97. And that's an example of a conformal tiling. It sort of motivated some of this more recent work. Now, if you go back to the traditional case, we have things that we're trying to emulate, but we're not there yet. First of all, in the traditional case, you get to look at pointed tilings. That is, you get to identify a point in a tile, sort of like a base point. We have a base tile, fine, in the combinatorics, but you need a geometric base point, because then you can slide a tiling, and so you can think of moving that base point around to get a family of tilings. But moreover, in this family of tilings, you have this big ball metric, so you can move continuously in that metric on the tiling space and in the translations. So we need that in the conformal setting. And I think I had something I intended to put in here and didn't have time. So let me think about this. PowerPoint doesn't automatically fill in what you want to say. Yeah, I wanted to say that it's really the terms in my title here. So for a given tiling, in the traditional case, I have these locally isomorphic tiling. So I have the big ball metric way of moving between a tiling and one which has different combinatorics. And I have the translations associated with moving the base point of my tiling. And so this gives what they call the continuous hull of the tiling. So the idea is that I have a continuous hull of the tiling. Let's think of something it should be suitably abstract in your mind, but I have this sort of hull of the tiling, and they have a cross section, a Cantor set sort of cross section to represent the equivalence classes of all the combinatorics. And you get to move around this space in two ways, by moving the base point and also by moving in the metric, this big ball metric. And so the question is sort of, as you move around this space, what equivalence classes of combinatorics are you going through? And so there's a sort of dynamical system associated with this continuous hull. And then there is a lot of study of C-star algebras associated with that system. So for me, these are just buzzwords until we can figure out how to define the continuous hull, whether we can get a dynamical system, and that's where perhaps this spherical metric on our tiling may come in. It allows us to define a base point again, which is conformally well defined. And then we can start mimicking some of this. C-star algebras, I don't know. So I wanted to go into an example. It's not going to give an example of this setting, but a slightly different setting. And so I want to try to talk about these ends a little before I'm done. So here's another subdivision rule. This is the snow cube subdivision rule. You break a quadrilateral into 13 quadrilaterals by this rule. And so what I'm going to do is that, by the way, is a conformal subdivision rule. So I've built it here. What I started with, if you can see these dark lines, I started with a cube on the sphere. So I started with 6 quadrilateral faces. Conformally, those are conformal squares, each a reflection of the others on the sphere. So this is a conformal subdivision rule, so I break that cube into 13 so that the subdivision is the blue lines here. So for example, right in here you can see the central one of those 13 subtiles on the subdivision of this this face on this side. Now the green is a subdivision of each of those 13 into 13 more. And then I think there's one more stage of subdivision before computationally sort of ran out of gas here. But the idea is that that's a conformal subdivision rule, so those are conformally correct tilings at every stage. And so at each stage you can subdivide each of the rectangles according to that rule, and you see that subdivision in place conformally. And then you can subdivide each one of those. And so you can think of driving into this, just dive down. Find some point and dive down into this. So I have many analogies. The Death Star analogy, as you approach the Death Star. I like actually the carnation can analogy, which only Americans of a certain age may know. But carnation cans used to have on them a picture of a cow with a can. And that can had a picture of a cow that had a can. And that had, so they too had to stop after about 4 stages. So I want you to think of diving into a point on this. And as you dive into this Death Star, the tiling looks more and more like the tiling lives in the tangent plane. As you dive in, the problem with subdivision is that it never stops subdividing. So you do the usual thing that you're familiar with. You go in and you extract a subsequence of these. So it's like going in and scaling so that the tile you happen to be looking at right then has diameter 1. So you dive into the next subdivision and you rescale so it has diameter 1. And then you extract from that an infinite tiling. So you actually have tiles to look at. Okay, they haven't become infinitely small. So those tilings are attached to tangent planes here. And so certain points, you'll get certain types of infinite patterns as you dive in. And so I did a little bit. I didn't have the computational horsepower to get this very far, but we start with this tiling. We dive in, and then we subdivide again just to try to keep going. Oops, sorry. And so this is, to me, where some connection with the type of randomness comes in. These are very deterministic when you subdivide, but finding these limits, extracting these limits from these expansion complexes, these combinatorial and conformal hierarchies, means that actually any piece of this, take any piece you like of a tiling, no matter how many tiles, and ask what global tiling it came from. Well, there are uncountably many global tilings this could have come from. So on that sphere, there are a few symmetries because I started with a cube. So I had a few symmetries there. But once you get away from those initial symmetries, that in the limit tilings, those are all hierarchical, aperiodic tilings, all locally isomorphic to one another, but any piece of any one of them could have come from uncountably many infinite patterns. So it's like you have this very deterministic looking thing at each stage, but you know ultimately that there's ambiguity about where this came from. So that ambiguity lives sort of in this hull. There are all your uncountably many tilings. You start out at one and start moving around, and you're hitting other versions of this tiling which have different endpoints. So whether you can interpret some kind of ergodicity here in some limit measure as a probability measure, I have no idea. That's over my pay grade. Those are the things, though, that I would like to, that's what I brought this here to point out. There's something a little different going on here than when you randomly triangulate something. What you have is an apparent sort of deterministic process, but it's at the ends of it, when you extract these infinite limits, that you're getting the uncertainties. And so I hope that it may attract some interest. I hope that we can push this so we get more parallels with the traditional theory, and we can describe this hull and the dynamical system more completely. My final slide shows that there are certain special cases in these. And so here, if you dive into that sphere, and you sort of pick certain points, this point is the same as that point at a later level. That's the same as that point at a later level. If you follow and continually choose to focus in next at the same local configuration, then in the limit here you get what we've called supersymmetries, because they're symmetries in this two-ended hierarchy. And so it turns out there that the subdivision rule is implemented by applying a Möbius transformation. So you actually apply a Möbius transformation. It takes your tiling at one stage, puts it in as a tiling with smaller tiles, but which exactly fill out the tiles at that stage with the subdivided tiles. And so this is a particularly nice hierarchy, but what you expect in general is if I pick a sort of random point on the sphere and fly into it, what is the rescaled infinite pattern that I get? I'd also like to say that this theory, which is new and is just developing, is sort of hovering somewhere in between the traditional theory. It has parts of that. But the actual target, in part, is the Cannon, Floyd, and Perry program to work on Cannon's conjecture. Cannon's conjecture has to do with Gromov hyperbolic groups that have a sphere as their limit in infinity, and the question of whether each of those groups is actually conjugate to a Kleinian group. So they look at these kinds of patterns in their finite subdivision rule work. And I say it's hovering sort of in between these because we're trying to mimic the subdivisions which live in place, these conformal subdivisions, their subdivisions are typically not conformal. So are you going to get the same type of information by pursuing these conformal tilings in their setting? And what it appears to be is that, in some sense, even when you have subdivision rules that are not conformal, where the breakup of a tile doesn't live in the same geometry as the original tiling, it still appears that there are limit shapes that come out. And that's the kind of things that their program requires, to understand these tilings, whether in the limit these shapes fill the Euclidean plane or the hyperbolic plane, for example. And so this theory is new. It maybe has some connection with things you think about. It certainly has some of the tools that a lot of you are familiar with. And so that's why I brought it here, and I thank you for the chance to talk about it.
Questions?
Yes.
So with the diamond tiling, there's a way that you can visualize it as a sort of height function. Is there anything that you can do with this that somehow can give you surfaces?
I don't know. Yeah, well, many of the dimer tilings come about in different ways. So whether a subdivision rule generates those. Now, we get dimer tilings in that a pattern and its dual, along with those, is that quad pattern of tilings. But that's a different thing. And there's subdivision; those don't persist. So I'm not sure whether I've seen dimer tilings in a subdivision setting, where the height information would be helpful, or where I could say anything about it.
So have you ever tried to consider doing statistical physics on these lattices and thinking whether there's some question that's either more interesting or more tractable or something in one of these pictures than would be on a grid?
I've never have, and it would be nice, but right now we're sort of experimenting and figuring out where the theory, how to complete the theory, and so we have sort of a complete package, and then to find applications, aside from the Cannon, Floyd, and Perry work, which drives us in a slightly different direction in that you want to look at the limits of the conformal structures when you don't have this nice conformal subdivision rule. So no, I haven't. There's certainly beautiful pictures, and something in there that attracts the eye is somewhere between regular and not quite regular, because they're never the same. So
what about random walks on these? Do you know if those approximate sort of the conformal structure induced by random walks? Is that?
Well, I think some of the standard results about those that we know live in the plane, for example, you can say some things about the random walks being, transient or recurrent, depending on the geometry of the tiling. So when you have locally finite combinatorics, you can use some of those connections. What we don't have, for example, is things with growing degrees. So in random triangulations, for example, you don't have bounded complexity. And so some of those questions become much more difficult, as people here know.
Any other questions?
Maybe you said it, but if you have a subdivision rule, can you tell if it will be conformal?
No, we don't yet have criteria. We have certain classes that, we're using to show examples, but we don't have a general theory about whether or not something is conformal. There's another part of this that I mentioned when they're not conformal. So if we went back, for instance, to that Sphinx one, I said in the Sphinx one, this is a problem. In this setting, this is a problem because when you subdivide it, the aggregate no longer maintains its shape. But darn, it's getting pretty close, actually, isn't it? And so in the first paper in this series we're writing, we show in many examples that although the subdivision thing does not have the same conformal shape as its parent, it seems to take the correct shape in the limit. So if you look at the Penrose tiling, for example, rather the pinwheel tiling, that pinwheel tiling is quite fascinating because of the geometry in here. You know, this is 1 by 2 by the square root of 5, so in the conformal version, if you pick out a triangle at some, and the way it was subdivided, so a triangle may have been subdivided many times, but you look at the aggregate, the original tile, all the pieces that came from that tile, and you look, for example, at the corners and their side ratios of the triangle they form, it seems to converge quite nicely to the ratios here. In the Penrose tiling, those are not nice darts. They're convex, in fact. But if you subdivide and look at the shape of the piece, subdivide just 3 stages, it's starting to form a dart with almost exactly the correct angle. So in a sense, the combinatorics seems to, in itself, because these come purely out of the combinatorics. So the combinatorics themselves of the subdivision rule seem to encode the geometry that they saw traditionally, and whether we can bring that out as a limit of the geometry you're seeing conformally is a question that may help link us back to the Cannon-Floyd-Perry work. So the conformal ones are very nice for mimicking the traditional theory more closely, but we really want to go that next step to look at the ones that are not conformal and whether you still get information out.